So now that we've seen how to make radicals, let's look at the structure and stability of them. And we're going to start off thinking about the carbocation. So we've already seen the structure of the carbocation. We know that it is trigonal planar and that the bond angles are 120 degrees. And so it takes on this planar geometry where you have an empty p orbital. And of course, the hybridization of this carbon is sp2 hybridized. Now, if we look at carbanions have quite a different structure. Because of that lone pair of electrons, the shape of a carbanion it looks to be more like a trigonal pyramidal geometry. And so the orbital in which the lone pair of electrons resides in happens to actually look more like an sp3 orbital. And so we say that carbanions, instead of being sp2 hybridized, are sp3 hybridized. If we think about radicals, the difference between a radical and that of a carbocation and carbanion is simply one electron in either system. So radicals have to be somewhere in between the shape of a carbocation and that of a carbanion. And when we think about it, we can think about it as being either sp2 hybridized, so it would be trigonal planar, or sp3 hybridized, in which it would be trigonal pyramidal. Now, it's very hard to really see the shape of radicals. It appears that it's somewhere in between, where it's either trigonal planar or it happens to be doing what we call an inversion between the one particular geometry of an sp3 and the other geometry of an sp3 hybridized carbon. So you have what's called this shallow pyramid that undergoes this interconversion. For our sake and for simplicity's sake, we're simply going to treat it as an sp2 carbon because it appears to resemble much more of a trigonal planar geometry than it does this shallow trigonal pyramidal geometry. Now, in terms of its stability, radical stability, we see that, like carbocations, the more substituted a radical is, the more stable it becomes. And we can see this by looking at methyl radical versus ethyl radical versus an isopropyl radical versus a tert-butyl radical. So here I have four radicals. I have a methyl radical versus a primary versus a secondary versus a tertiary with the tert-butyl radical. And I can examine the carbon-hydrogen bond dissociation energies in order to get to this radical. So if I take methane and I cleave a carbon-hydrogen bond, dissociate it to get a methyl radical, the bond energy of that is 440 kilojoules per mole. Likewise, if I take ethane and homolytically cleave a carbon-hydrogen bond, that bond dissociation is 423 kilojoules per mole. So notice the bond dissociation energy of a carbon-hydrogen bond is quite a bit higher than that of a carbon-carbon bond. Right? So carbon-carbon bonds of ethane are 376 kilojoules per mole. Carbon-hydrogen bond dissociation energies are 423 kilojoules per mole. Right? So just to put that in context of what happens when you add heat, you get carbon-carbon dissociation, typically speaking. Now, if I look at the isopropyl, the isopropyl radical, I see that it has lower energy, 413. So as we go from the methyl to primary to secondary, the dissociation energies are decreasing, and when we get to the terbutyl, it has the lowest bond dissociation energy. And so we say that terbutyl radicals are more stable than, tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals, which are more stable than methyl radicals. And this, again, follows the trend of carbocation stability as well. So it should make it relatively easy to remember the stability of radicals. So the reason for this happens to be the same as the reason for carbocation stability, namely hyperconjugation. So if you recall, back in chapter 1, when we talked about stability of carbocations, we looked at the a carbon bond adjacent to that carbocation. And so I'm simply going to highlight, if this was a carbon-hydrogen bond, that bond, if it's in the same plane as the p orbital, it can overlap with that p orbital, right? And in the case of carbocations, we see obviously that carbon-hydrogen bond has 2 electrons. The carbocation has an empty p orbital, and we get this overlap that's occurring. So we get we call it slight sigma donation into that p orbital. And we can think about this in terms of molecular orbital theory, right, where we're taking a sigma bond, carbon-hydrogen sigma bond, and we're mixing it with that p orbital of the carbocation. And we end up with, obviously, a bonding orbital and an antibonding orbital. And because this is a 2-electron system, the 2 electrons coming from that carbon-hydrogen bond, we see that you can form this overlap, and you basically lower the energy, and that's what causes the stability of that carbocation. And so, so if I think about the radical, again, in the similar fashion, I have a carbon-hydrogen bond. I can draw that orbital, right, that sp3 hybridized orbital that's creating a bond between carbon and hydrogen. And so now in this case, the only difference is I have 3 electrons, and yet I can still think about donating those 2 electrons to help stabilize that radical. Again, if I look at it molecular orbital, at the molecular orbital description of it, I can take that carbon-hydrogen sigma bond, mix it with the p orbital of the radical. And so the only difference being is now I have 2 electrons of that carbon-hydrogen bond, and I have 1 electron in the p orbital. And so we mix them, we get bonding and antibonding orbitals, so to speak. And so now we place 2 electrons in the bonding, and 1 electron goes into the antibonding. And so we see that obviously the hyperconjugation effect isn't going to be as great as that of carbocations because we have 1 electron in an antibonding orbital. But overall, there's still a stability that's provided. And I would direct you, to think about other 3 electron systems that you have, we've discussed, namely that of the helium-2 plus ion, right? It's a 3-electron system. So now we know that the more substituted a radical is, we can also think about how resonance can stabilize a radical. And we've already seen this in the section 2 of chapter 12, thinking about alkenes and their stability. And so if we compare the most stable tert-butyl radical to that of an allylic radical to that of a benzylic radical, And again, we can think about the bond dissociation energies of the carbon-hydrogen bond to get to these radicals, right? So I'm taking 2,2-dimethyl propane, and I'm removing an electron, a hydrogen. And in the case of the allylic radical, I would be taking one propane and removing that hydrogen off of the methyl group. In the case of the benzylic radical, I'd be taking toluene and removing a hydrogen off of the methyl group. And the bond dissociation energies are known for these reactions. We've already seen the bond dissociation of the tert-butyl radical as 404 kilojoules per mole, so this is still 4 kilojoules per mole. And you see that the allylic radical, even though this would be considered a primary allylic radical, is substantially lower in energy than the tert-butyl radical is. Likewise, the benzylic radical is also lower in energy, even though it's a primary benzylic radical. And the reason for this has to do with resonance stabilization, right? So again, I'm going to stress this to get you used to thinking about, how do you draw resonance structures? If I take that allylic radical, I can donate that electron and take an electron from the that pi bond to form another pi bond, and that last electron then goes to the carbon on the left, and I generate an equivalent resonance structure, right? So these two resonance structures are definitely in equilibrium with one another, and it stabilizes by distributing that lone electron. You can get stabilization. Likewise, with the benzylic radical, we've already seen, and so I'm going to go through this rather quickly, but you can look back in your notes, and you see that you can generate various resonance structures, right? So this is the first resonance structure. Again, another allylic system, which I can then move my electrons around to form that second resonance structure, which I can then move my electrons and form my third resonance structure. So because you have, again, this delocalization of electrons, you see that these types of radicals, radicals in which you have a pi bond that is adjacent to the radical, certainly is much more stable than a typical alkyl radical.